This video is to go over building Java programs through the Practice It website. We're looking at the Binary Trees Chapter 17, Exercise 2, Count Empty. So first of all, I want to say that I've done two previous videos that you should have watched before you get to here. First is the self-check 1711, which I have the full code for to show you how to get the size of this tree. And then 17.1, I gave you the pseudocode for how to do it. And I'm going to rely on that knowledge as I proceed here. So similar to 17.1, 17.2 is a bit of an odd duck. It's not a really useful feature. It's just a good exercise. So instead of looking for left children that was in the 17.1, now we're looking for empties. And what's an empty? An empty is something that's not there. Again, so that's kind of funny. It's not something we normally care about. But so anytime that you have something that's not there, you don't have a left or you don't have a right, that's what we were trying to count. So in this diagram, everything that's got a little circle here is an empty. So it's very similar to 17.1. I'll give you some pseudocode here. So first of all, you're going to need to call a helper function because these are member functions, so it's not going to take any parameters. In order to recurse, you're going to need a member function that's going to pass down what the current item is. Now, just like in 17.11 and 17.1, we are going to have a base case for when the tree is null. And then we're also going to have a recursive case. So it's a little bit different, though, because whereas in the two previous examples, when we got down to here and we got to null, we were trying to count things, and so we were just returned 0. But in this case, we actually want to count this guy, right? Anytime that we come down to a null, whether it be on the left or on the right, that is actually what we want to count. So unlike other examples, now what you're going to need to do is you're going to actually have to return this as a success. So you have to return, you got to return 1. Because if you don't return 1, it's never going to get counted, right? In the recursive case, it's actually simpler because before what we were doing is we had, for example, in 17.1, we had to check to see, do we have only a left child? And if so, we would return 1 plus the recursion. And previously in the size, we would just always add 1, and then we would recurse left, and we would also add in the recursion left and the recursion right. So we're always going to want to recurse left, and we're always going to want to recurse right here. There's no exclusions for whether it's just a left node. So we're always going to want to recurse left. And then we also need to recurse right. We've always got to do that. There's no if statement here. And but unlike size, where we were always adding 1 when we recursed, we're not going to always add 1 because, for example, in this top level here, we don't want to add 1 for this because it doesn't have any children. So as I mentioned already, it's only when we find a null that we're going to add 1. So you're going to have to return. You have to return something. You're going to have to return the result of recursing left and recursing right, and only in the cases when the base case comes down to a null are you going to want to return 1, and then that will be added in when it returns from here. So let's see whether this actually makes sense that it's going to work. So we're going to start here, and then we're going to check to see whether it's a base case. It's null. It's not null. So we're going to recurse. We're going to add whatever recurses on the left and whatever recurses on the right. We're going to come down here, and it's not null. So we're not going to return 1. Instead, we're going to recurse. We're going to add whatever recurses on the left plus whatever recurses on the right. Now, we'll skip for the left here for a second because the right is the interesting case. So then we get down to recursing on null. And so we immediately say, hey, it's null. So we got to return 1. So this guy up here is going to add whatever is the value of this plus this 1 here. So let's go all the way down here because this is all the same until we get down to here. So on the left-hand side here now, we get here and we say, oh, it's not null. So we're going to add whatever's on the left and whatever's on the right. So when we go down to the left, it's going to say, oh, it's null. It's going to return 1. And whenever it comes down here, it's going to go, oh, it's null. So it's going to return 1. So this guy is going to return 1 plus 1. So there's 2 of these empties. And that'll pass it back up here, and it'll add in this third. I'll pass it back up here, add that fourth, pass it back, blah, blah, blah. So this should work. So I'm not going to give any more code, but if you take a look at how you've done 17.11 and 17.1, you should be able to write the code for this. What have we learned from this over what we've learned in the past? Well, there's this odd duck case of looking for the empties. In this case, it's a slight variation where the base case, when we get null, is actually where we're returning the data, the 1, whereas before we'd be returning 0. So it's not always returning 0, could return null, whatever. But we're actually traversing the binary tree in the exact same way as we've done in the past. So if you found that useful, please like and subscribe.